solution for downstream fish migration. Well, thank you very much for this introduction. I will now try to present to you the current state of the art in France for downstream migration. I will also touch upon the technical side and what research looks like there. I would think that there has been research in this field since for 25 years now. Michel Travat and Larignier, they did a lot of work in this area. You may know them. And I think there are a lot of similarities to the situation in Germany. Let us look at the legal environment and the technical solutions available in this legal framework regarding turbines. Of course, you can stop turbines. Then you can use physical and sensoric behavioral components. But let us first look at the legal framework. In 2006, a new law on water and aquatic environments was introduced. A list of waterways was compiled, waterways that are important for fish migration and the transport of sediments, and a term started in 2012-2013, a term of 5 years, to make sure that the existing structures in these waterways are adjusted in a way that fish migration is made available. So we have time until 2017-18. And out of these structures on the list, it's 15,000 structures. We found that about 8,000 still need to be equipped with installations for upstream migration, and, which is even more important for us, 1,000 of these structures need to be equipped with solutions for downstream migration. In France, we mainly focus on smolts, but also sea trouts, the size 15 to 20 centimeters roundabout. So as I said, trout smolts and salmon smolts, but salmons also at the adult stage. So we mainly focus on these species because they swim close to the water surface and have to overcome many hydroelectric power station barriers. The actual mortality rate is not so high, but because of the high number of structures they have to pass, it is increased. Furthermore, we also focus on the eel, also the silver eel, where mortality rates are very high. Mortality during downstream migration, this mainly holds true for the females, which spawn in the rivers. They are between 15 and 90 centimeters long. The males mainly remain in the lower parts. They are 30 to 45 centimeters long. We don't focus so much on them because they do not have to pass so many obstacles and barriers, and therefore their mortality rate is lower. Regarding the other species, they are all diatromous species like the Alice shad, the Alosa agona, and so far they have not been such a great focus of attention because, for instance, the Alice shad does not have to overcome so many obstacles, so there are not that many problems with them, and their mortality rate when passing the turbines is not so high. At least this is what the results of US studies indicate. We are also running respective studies now in France. The areas where Alice shad and lamprey live are also passed by eels. These species are protected altogether. Then regarding holobiotic species, we do not really focus on these species because they don't cover such long distances and the mortality rates when passing the turbines is not so high. We do not know exactly at one stage of their life they migrate, and this makes it hard for us to design respective facilities for them. When talking about eels, I said it already, we're talking mostly about smolts, and for the other species we have no specific solutions. But we are also focusing on solutions for trouts, where mortality rates are high regarding the downstream movement. Now, what are the solutions? One solution is to temporarily stop the turbines whenever there's fish migration. At least this is what we considered for the eel. But as a result, you have a production result on the operator's side if they have to stop the turbines for a longer time. And therefore, you need to know when the fish migrate. You need to anticipate this to be early enough if your turbine stopped. Respective tests have been conducted with regard to early warning systems like the micromode. This makes it possible to anticipate when the fish migrate, but the efficiency is rather low at about 30%, and the early warning system is too late. It is too late when the early warning system indicates the migration is done. It's too late to stop the turbines. Further studies were conducted on whether the temperature, turbidity, meteorology, discharge, and so on, whether this has to do with migration. We do this mainly at the Tuyer and Dordogne rivers. In some cases, we stop the turbines for 40 nights. This has to do with hydrology. This causes high costs and makes the use of certain devices for early warning systems necessary, and we are not quite sure whether these systems can be transferred to other waterways. And there are also other waterways where we decided to stop the turbines, but there no empirical results are available yet. Then fish-friendly turbines are an alternative. There are two kinds of these. We chose in France the very low head turbine. And these mainly work well for the sea trout and salmon. And you can see it here on the picture upright. But then we also have the screw pumps, Archimedes screws, between 1 and 10 meters wide, but it's rather dangerous for the fish. And here, further protection is needed to make sure that the fish do not get in contact with the screw. So we must by all means avoid any contact. We don't have pentaturbines yet. That was mentioned before. No tests run yet with a pentaturbine, but the water wheel, this is also a solution, but we haven't tested it yet. Then I want to talk about the sensoric behavioral barriers. These are systems working with light, with electricity, with sound. We tested it in the lab, but the in situ results are rather bad. So low efficiencies depends highly on the environment in which these systems are placed, and so far we cannot implement this solution yet in France. Then there's this lighting bypass solution, a light signal to attract the fish into the bypass. However, the efficiency here depends highly on the flow situation, so that the fish easily find the entrance of the bypass, and when the flow is low, then the size needs to be bigger. And we also carried out infrasound tests as behavioral barriers. That was conducted between 2008 and 2009. And we used badges there at a height of 30 centimeters on the wall to find whether the sound, the infrasound, causes the fish to choose a different path. But we found that no, the results were not so good, so therefore we no longer focused on this solution. Let us now look at physical barriers for behavioral solutions. There we have the hydrodynamic protection walls, louvers, kinds of screens at a certain slope to the riverbed, but they can also cause turbulence. So far, we don't have such mechanisms in France because of the congestion problems, and they need to be sealed very well and so on. And this is one of the reasons why we don't have these in France. Then other possibilities are walls that are installed to guide the fish. This mainly holds true for these salmonids, but also only at depth between 8 and 10 meters. We installed some kind of surface mask over a size or surface of 4 to 5 meters. And when the smolts are descending, they are guided over this mask. This is between 3 to 5 meters long. There are 3 entrances into the bypass. And the first results for smolts were a real deception, but then we made some adjustments regarding the flow pattern, and since results have improved slightly. For the eel, these system with the wall as guidance systems don't work. And in France, we thought a lot about screen systems and bar systems. Since the 1990s, their efficiency is rather high for smolts. The rate is between 10 to 20, but up to 80% even. But it always depends on the clear width of the bars and the flow pattern. Here you see some examples from Halsou in the River Nive and Poutès, the River Allier. And studies show that it was often necessary to improve the flow pattern in order to increase the efficiency of the bypass system. Castro Santos also showed that yesterday. This is a similar system that you mainly have to work on the entrance and offer fish ways to get into the bypasses. We have a first bypass here, which was rather far away from the actual screen. The flow was rather low, and there we had an efficiency of 20%. Then we adjusted this, reduced the distance. Then we had the flow directly before the entrance to the bypass system. This flow was reduced, and as a result, efficiency was significantly increased. But I'm aware that the result is still rather moderate. We conducted about 15 tests in France, and you may have heard about them or seen test outcomes. In some installations, the results are not so good. Sometimes we have efficiency rates of 60 to 70%, percent, and in other cases, in Gave de Boue, for instance, or Ariège, there the results are more satisfactory. So we took all these results as a basis for improvements or considerations for improvements. In some locations the systems worked well, and others not, and so we thought, how can we make adjustments, and what criteria can we define here to guarantee functionality? So we found that we need a bypass system that is combined with a screen. This reduces mortality rates, but it does not work in all cases. And also for salmon, the results were not so good. And I said it before, we also tried to draw conclusions from the results. We also looked at the test results with these screens from the US and Canada, and on this basis we chose criteria for efficiency increases to 80-90%. This is all related to the fact that you build in a system that leads fish into the bypass. So we need a physical barrier with a clear width of 25 millimeters bar distance, and for salmon it's 15 to 20 millimeters, and the average velocity is 0.5 millimeters per second. Of course, the fish's ability to swim differs a lot, and this must also be taken into account. Furthermore, the screen must have a certain slope, and like in Germany, we prefer two designs, either a vertical screen with an incline of maximum 25 degrees, and then we also have a vertical screen with a slope set at an angle of below 50 degrees. It is clear it is important to introduce this guidance system and to efficiently guide the fish into the tailwater. If the fish is stopped, then of course mortality rates increase, and they are then higher than if the fish pass the turbines, and thus this must be prevented by all means. Now, criteria regarding construction or design. There we have criteria regarding number, size and velocity. When it comes to the inflow into the entrance into the bypass, because this has an effect on the flow velocity within the bypass. Let us take the inclined screen with a channel. There we set or defined velocities that are slightly higher than the velocity at which the fish are arriving, because we want to make sure that the fish do not have to decelerate but can continue at their speed. We need a water depth of about 0.5 meters to make sure that we have a water buffer here, and you also see the flow pattern on the right, this colorful picture, and this shows what flow pattern is needed to attract the fish into the bypass system. And this way we could also define how wide the entrance needs to be and what distances we need between the bars, namely between the screens, 4 to 6 meters. And if you know the different parameters like velocity and dimensions, then you can calculate the required water volume or flow volume. I know there's a lot of discussion about that. It has an influence on the fish or the number of fish using these systems. So we if we have smaller facilities, we have lower values. You can see that from the table down there, and we found that at a flow of 2 to 3%, we usually have a flow of about 30 cubic meters. But for other installations, we do not have exact values. Let us come to the conclusions now. 2 to 3 fish species were taken into account for the study: the eel, smolts, and the sea trout. And 1,000 hydroelectric power stations need to be retrofitted over the next few years. And this is a big challenge. We expect that 2 solutions will be acceptable for those with flows of up to 100 cubic meters. This would be the screw and the turbine stop. And then for other installations, there would also be other solutions like screens. You can, of course, if you have a screen system already installed, you can keep it and install an additional bypass system. But for this, you need a larger clear width, and as a result, you would need an adjusted bar cleaner or screen cleaner. And if the fish are not adequately guided or led into the bypass system, then you need to make it wider in order to reduce the deficit here. For the smolts, the flow pattern is also of major importance. The screens need to be changed in design in some cases, because if we find that the fish are abruptly stopped, then we need to adjust the dimensions and the design of the screens. And for hydroelectric power stations of up to 100 cubic meters, we opt for inclined screens because this reduces the congestion rate, and this is also better for the flow pattern and for maintenance. Here it is easier to clean them. And we also found that the system on the right, the bottom there, that this system is very good for dealing with floating debris. We don't have an exact list of bypass systems installed since the 1990s. And now we have the new legislation anyway, and 50 installations have been adjusted or retrofitted to the new legislation. So at the moment we are a little lagging behind plan. Of course, we still consider or continue to consider how we can adjust screen cleaners to improve the results. Then stopping the turbines for a certain time is also a possibility, especially for eels. But there you need to calculate exactly the ratio between cost and efficiency. Then, in the case of the trouts, there are 2 possibilities. One, bypass linked to a screen, but this is only possible in a fish-friendly facility, and the bar width must be adjusted. And furthermore, efficiency tests must be conducted regarding the future outlooks. Regarding the inclined screens, we need to change the dimensions of the transverse channels. What is interesting for us are new bar widths to reduce congestion, and we are especially interested in the German horizontal screen system because we don't have them yet, or we haven't tested them yet in France. And then we also need other solutions for the bigger hydroelectric power stations. As I said, in the recent past, we have a value of 15 cubic meters for those installations that were built in the recent past with a basin depth of 7 meters. On the right, you see the bypass and the outlet of the bypass system. So we also want to avoid that ascending fish can be heard in this place. Here is a more recent example from 2013. An installation with a volume of 16 cubic meters per second with a basin depth of 15 meters. Then we also have bigger hydroelectric power stations with 54 cubic meters. And there the width of the screen must be bigger, of course. But this also has to do with the channel you install. So here again you see the inclined screens, trash racks in the River Ardèche. And a last example, at Barche-sur-le-Gave-de-Pau, we have a hydroelectric power station with 90 cubic meters per second. There we enlarge the embankment, and we now have a bar width of 30 to 20 millimeters. So that was it, and thank you very much for your attention.